Okay, we are right at the top of the hour, so we shall begin. Ladies and gentlemen, thank you so much for joining us today. On behalf of AUVSI, I'm pleased to welcome you to today's webinar, Applying Commercial Connectivity Success to Modern Warfare. My name is Nathan Hoback. I'm Engagement Manager here at AUVSI. Before we get started, just a few housekeeping items to note as usual. As always, all participant lines will remain muted during the webinar. We are recording the program, and a viewing link will be emailed to all attendees, along with a copy of the slide deck within the next week or so. You can now view all of our webinars on AUVSI's new learning and engagement platform, AVL. If you're listening to the broadcast and need some assistance, please send a note to the webinar leader using the chat at the bottom of the screen. After the presentation, we'll open up the session for a Q&A. Attendees, you're encouraged to submit questions at any time throughout the webinar using the Q&A button at the bottom of your screen, but questions will only be answered at the end of the presentation. Do please note, though, this is a different box than the chat, so please submit all your content questions using the Q&A, which can be found along that bottom bar. So let's get started. I'd like to welcome and thank Elsight for their support of today's webinar on this important topic. We are excited to have an excellent speaker with us today, Roi Kashi, co-founder and CTO of Elsight. Roi Kashi is a visionary entrepreneur and thought leader in the fields of BVLOS connectivity, scalable drone network operations centers, remote ID and network RID, and the Internet of Drones. As co-founder and CTO of Elsight, Roi is instrumental in the design and implementation of BVLOS drone solutions globally. And also, Roi was recently elected to co-chair the GSMA Drone Interest Group. So we are definitely in great hands today. And with that, Roi, I will hand it over to you to kick us off.
Thank you, Nathan. Thank you, AUVSI, for having me here in this wonderful webinar and this platform. And I'll start by saying that it's a little bit strange and difficult times, I would say, to talk about commercial connectivity and how it goes to the defense sector. But it is kind of the reason why I'm here today. And to be honest, if we talk about Elsight, and before I start with all the longer intros, up about a year ago, a focus was mainly on the commercial market. And when I'm saying commercial market, it's really from the parcel deliveries with the drone up from Walmart stores, sorry, and with ACSL in Japan, or with aerobotics with their FAA type certificate we have with the Halo inside, the Elsight communication system, and with Speedbird with their deliveries all around the world. But then things happened, and when things happened, what happens is that we started to receive significant orders also in the defense market, place that we almost never had anything significant in it. And what interesting is that we didn't do anything specific for defense. We didn't change anything in our product or solution, but it's quite the opposite. It's the understanding in the defense sector that in order to move quickly and with cost-effective solutions, they need to use the top-notch commercial solutions. And this is how we found ourselves providing our existing commercial technology as is to the defense sector. And basically, the idea of this webinar came exactly from this approach of understanding how we apply this our commercial connectivity solution as is for the defense sector. And it really opens up all kinds of different understanding about this market and what we do. So again, just doing another intro on Elsight and by myself. So I'm the co-founder of Elsight and the CTO. And like I said, we typically what we're doing is we providing BVLOS communication system to get connection confidence from drones, UAS in general, and for ground robotics as well. And this is really our bread and butter, and this is what we do in our day-to-day all over the world. And when talking about Elsight, then we already have more than 250,000 flight hours with our communication system. Like I said, we got also together with aerobotics, we're part of the FAA type certificate, and with different regulators in the world. This is basically what we do. And I want to go directly to one of the things that we noticed, and well, I'll talk about all kinds of different topics here about how we see the Internet of Battlefield and how we see the changes in the different sectors and the militaries. And I want to start with this because when we're talking about connectivity system, connectivity radios, uh, connectivity systems for militaries, then the main perception is that why would a military need a commercial radio? Um, and the main thing is that the military has the perfect radios. And with perfect radios, sometimes they're too perfect. Um, the idea is that when you plan a certain radio, you want to plan for the worst case. And with the worst case, you're doing something that is so good that sometimes it's too good or too special. And when it's not the biggest war, then you don't want to reveal all your cards. So you end up having the best technology locked in a safe, and you probably not tend to use it at all times because it just may expose the abilities that maybe you're trying to hide, like a never failing radio that can pass any jamming and so on, or just may fall through wrong hands. So you want to keep the perfect solution, but have maybe something that in a lower grade that is good enough for the operations that you want to do. And the second thing is that when you integrate commercial technologies, then you're actually free to go, free to use it anywhere on the battlefield. Again, without exposing anything, any secret and anything that you want to hide. So with this approach, we understand that we're not coming here to solve something that militaries or defense doesn't have, but we come to provide the exact thing, the exact solution, the optimal solution for these specific scenarios that we're talking about, the modern warfare that is not just in the middle of the ocean or the middle of the desert, but it's sometimes in urban environments, as we could recently see. So when talking about this shift or this request of solutions from the commercial sectors, specifically in the drone industry, it's very obvious because um, for defense contractors or the defense industry in its basic form, it is mainly targeted and mainly designed to build and plan a multi-year solution. So a certain solution will be planned, start today, will be probably ready in 2030 or even more. But when it comes to terror organizations that are adapting very quick and improvising all kinds of different solutions, then militaries need to find quick solutions, quick and innovative solutions now, not in the next year, not in 5 years from now, but literally now. And when we see this integration of commercial communication systems, for example, in uncrewed systems, then typically what we see is a single commercial radio. It can be a point-to-point or a mesh network, but a single communication, as good as it can be, um, it is still limited. It has its flaws in various of environments, and I'll start to talk about some of them. So when we're talking about the adopting of commercial solutions, then one of the questions is how a commercial solution can fit to defense industry, which is so complex and is like everything is so tense and very harsh environments. But when you think of it in the UAS industry and in the robotics industry, what happened is that because of regulation requirements and because of the main thing was how to create a reliable and safe operations and how to make it scalable and how to make it secure. And all the time, you want to ensure that the missions are safe in order to not abort the mission, in order to pass regulatory requirements. What happens is that the commercial solutions evolved very, very quick. And this evolution of having a reliable connectivity beyond visual line of sight with all of its technologies around for non-GNSS and for parachute systems and for vertical awareness and for all kind of tethered drones and all kinds of different solutions. And it only made sense that these top-notch, best-in-class solutions in the commercial industry was found valuable also for defense that needs exactly those things: reliability and safety and security. So when it comes to this, really, one of the things that is quite different between the commercial side and the defense is the concept of operation, which is quite different, because when you're talking about the shift to BVLOS in the commercial world, then it all comes with not only the immediate interpretation of beyond the pilot line of sight, but it comes with the understanding of having a control center that is able to control and manage multiple drones or uncrewed vehicles remotely outside line of sight. You can have the remote operator sitting actually anywhere in the world, but it is still quite new and different in the defense sector, at least with the simple UAS solutions, since there's still the pilot in the field. So with this change also of the CONOPS, you can see also adoption of the way things started to look in the commercial side, and started to migrate also to the defense sector. And really, this is part of the of entering the new era of the new CONOPS. And as an example, with Elsight solution, really what we found is, like I said, really hit the sweet spot here in terms of having a low swap size, weight, and power system, connectivity system. It's really cost efficient in terms of relatively to the high gear radios or military grade radios. And when we're talking about the solution, I'll explain it about, of course, in a second, then it changes the whole concept of how we actually able to operate a UAS. So it's not limiting the options, it's adding on top of the current options also new elements and new possibilities. So really, because what I'm going to talk about here is actual understandings from field proven experience with the Elsight Halo and really in the major conflict areas in the world right now. And today, what it sees that it's the Halo stands as the new optimal solution for the defense industry because of this need and connection confidence for uncrewed systems and the security, redundancy, and scalability. And I want to start and talk about what do we mean when talking about having connection confidence. And it all goes again to this really challenge, I would say, of having a connectivity not only beyond line of sight, but also within line of sight. When we're talking about the battlefield or the modern warfare, then connectivity becomes a real challenge. And when connectivity is a challenge, you can't rely on a single communication system. So the idea here with, I would say this is the best practice with or without a Halo, to use multiple and as much as communication paths as you can. So for example, let's say we're in a US and we want to control the drone remotely, then why not, in addition to the point-to-point SDR that you might have, let's add also T-Mobile 5G network and Verizon LTE and AT&T public network. And you can combine it also with, for example, Lockheed Martin's 5G.mil private 5G site, or combine it with Starlink or with Iridium or Inmarsat solutions. The idea here is to have multiple paths as possible. The more paths you have, then you're more resilient to jammers, you're more resilient to outages in different technology providers. You're more resilient to I would say changes in terrain. For example, you can move. You have much more flexibility in terms of building the path of the drone or the unequipped vehicle, because you not depend only on line of sight of the SDR with or without repeaters on the way, but you're really able to have a more flexible radio environment. And it's one of the things that we're seeing in the industry, which is not quite ready today, but it is something that we will probably see in the near future, is the ability to use also LTE and 5G over satellite. Again, there's a lot of different companies that are entering to the LEO-based, the LEO satellites, and not using any of these constellations, it would be really it won't be a good idea. I mean, basically, at the end of the day, what we want to have is as much possibilities as possible to get these redundancy, if it's path redundancy and technology redundancy and frequency. So talking about how to actually implement it, then you can't really have just multiple paths and start transmitting data to multiple different destinations, or through or let the application start and use different communication paths, because then you'll just go to a very long development customizations with each of the vehicles. So what you want to do is to take all of these communication paths and make it look to the user, to the application, as if there's a single pipe. And this is really one of the things that we do in Elsight. You can create this connection confidence only by having a logical layer of connectivity that encapsulates everything inside. So if one or some of the communication paths are failing, then they are failing internally. There is no disconnect at the application side. You won't lose the control of the vehicle, and the video won't stop, because you have a logical layer that is able to duplicate and steer the traffic between the available paths. And this is really the main idea of how things should be done. And there are certain aspects of it. For example, how do you secure internet-facing communication paths? So one thing is that not all deployments and not all missions are top secret. Sometimes, and most of the times, even most of the operations are not the top secret ones, and you need communication solution also for them. But one of the things that you're able to do to secure the communication is adopting a double VPN approach, having having a certain VPN from the field, from the vehicle to the station, and then having another VPN with a different key or different vendor to establish its tunnel inside the outer VPN. Having this double VPN approach makes it very secure. The second thing that is important to understand is that when we're talking about multiple paths, not all of them go to the same pool. Not all of them are internet facing, for example, or go to a certain server. some of them are staying local, they're point to point. And when we're looking about this kind of approach, then there's a couple of things that needs to be understood, and it's how to connect these different communications. And so I want to start with one diagram, which is how this just simulation of how the data dispersion is go and just a split across all the radius spectrum here. And again, this is just a small simulation of a drone that has multiple different radios on it. It has the point-to-point SDR or mesh network, for example, and it has a certain private network for like a 5G network for CBR on CBRS bands, for example, and maybe it has also satellite communication with one of the vendors I talked about, and it can also use probably public commercial networks such as Verizon, AT&T, and T-Mobile. And once we're able to split this data across all different paths, not only you get the redundancy, and not only that you get the high availability, but you also get another side effect, which is another layer of security, because we're actually splitting data to multiple different paths. Then having someone being in the middle, it just gets pieces of secured pieces of data and doesn't get the full data. So again, this is layers, different layers of security or different values that were designed and are true for the commercial industry, but they're true as is and relevant as is for the different sector as well. So when talking about the public communications that needs to be aggregated or combined with point-to-point communications, then something here doesn't really make sense, right? I mean, one data goes to, for example, with T-Mobile to the internet, and another communication is point-to-point with an SDR. So the idea here is how to create a soft handoff between siloed networks, like a data path or telemetry or video stream that starts from a public 5G internet, 5G communication, for example, and then handoffs seamlessly to the point-to-point SDR. And it can happen only if you have the a device that will duplicate and deduplicate the streams in both ends of the mission. For example, having the Elsight Halo on the UAS to read the telemetry and or the video, and then it's able to duplicate the data, and then one copy sent through the LTE or 5G communication to the server, and from the server send it back to the ground halo for the operator. But then there's a parallel link that connects the aerial halo with the SDR or with a private 5G site, directly send like the second copy, send it through these communication lines to the ground halo, again, directly through the point-to-point communications in the private network. And then the ground halo is then able to get these two flows or multiple flows, one from the public network and the others from the private networks. And then it is able to deduplicate the streams and forward a normalized stream to the GCS, the ground control station. And this ability is really a game changer, because it allows you to instead of replacing your network or replacing a certain way of how military used to operate with SDR or in the point-to-point network, it actually, instead of replace it, it's adding on top of it additional abilities. And this is really what we're talking about here. It's not changing or replacing existing solutions, but enhance it. If today, for example, a certain SDR is limited to a certain frequency or a certain bandwidth range, with adding this logical layer of connectivity that can encapsulate multiple different communication paths, you're actually adding more technologies to it. You're adding more frequency ranges, you're adding more bandwidth, or having different applications send different data through different communication paths in different priorities. It's really limitless, the amount of options that you have here. And again, by having this kind of setup, what you can really see, and these are things that we've done a lot also in the commercial market and then in the defense industry, is the ability during a mission to cut the SDR connection, and then you'll still see everything works, the telemetry and the video, just as long as you have any of the available paths working, it will still work. And this is really one of the most important things to understand here. Now let's talk a little bit more about the Halo. So with our Halo, what we're doing in Elsight, we have our proprietary bonding solution, which means that this is the secret sauce, let's call it, of how to get all the communication paths and combine it into the single logical layer of connectivity. And this is how we're able to connect the LTE and 5G, the public and private communications, together with the external satellite communication types and with local point-to-point SDRs. And what we're getting is really a continuous connectivity. As long as one of the paths are working, you still have a reliable communication, regardless if some of the paths are jammed or some of them are blocked by terrain or just a long distance. By having this variety of communication paths, you're just getting a much higher chance of completing the mission successfully. Like I said, there's the soft handoff between the siloed networks. And one of the things that we have here is also the ability to automatically map the cellular signal levels in the operated area. So just by turning on the Halo and having any source of position, what we're doing is we automatically generating a CSV file that contains in 1 hertz, it contains the position together with the pitch, yaw, roll angles of the UAS and the RSIP, RSSI, RSIQ, and all the information from all the different modems and SIM cards, and upload it to your environment. So really, this is a very a useful feature to understand what is the situation of the RF signals in a certain area. And of course, we design in Elsight this solution for UAS, means that it comes with a very low in power and low in weight, just in order to, and of course in size, just in order for you to have this kind of solution sitting on a UAS. Now I want to talk a little bit about a few use cases that we've seen, and one of them is, of course, just to have a US connectivity for ISR missions outside line of sight. And of course, we're talking about the outside of radial line of sight in this aspect. So it's what, again, shifting from the commercial industry, where what we went through is with the BVLOS, the regulatory terminology of how do you operate beyond visual line of sight. In the defense, the BVLOS is not that important, but it's the no line of sight, the more the technology aspect of it and not the regulatory aspect of it. So I would say the main challenge here is when you need to operate beyond the radial line of sight, the SDR, standard SDR, will most probably fail. Once it loses the line of sight, then SDR are not meant to work this way unless you have, of course, a mesh network with more nodes and relays in a network. And by again changing the CONOPS, changing the concept of operation, and stating that you don't necessarily need to have line of sight with the radio, but you can also extend and enhance all the available spectrum in the area with, like I said, combine it with public cellular, for example. In most chances, when you work in urban environments, for example, then you will have, and also with few kilometers around it, you will still have public cellular communication, and will really, there's no reason not to use it. So, for example, let's say that we're in a place with and we lost the SDR connection, but there's still signal of Verizon, AT&T, or T-Mobile. Let's use it with LTE or with 5G. Let's use it. Maybe we lost also the cellular signal. Let's see if we have satellite communication, whether it's in parallel or whether it's in prioritization. But again, there's many satellite constellations, different options. If it's GEO or LEO constellations, as long as you have this kind of communication and you have the right modems on the UAS, you're able to use it, encapsulate it within the logical connectivity layer, and then the mission one abort. And of course, what you're gaining is that as long as any communication path is active, then the C2 and V2 remain on. And this is really, again, the main message of what we're saying here, not replacing the SDR, not replacing the point-to-point, but add more communication paths on top of it. Another a very similar use case would be just to have a resilient US connectivity in jammer-rich areas. So maybe it's not beyond line of sight. Maybe it's within line of sight, but in a place with a lot of jammers, then it becomes a real challenge to operate with standard commercial radio communications and radio systems. And again, when we're talking about the Halo as a solution to it, then the Halo itself doesn't come with our own SDR or with our own point-to-point radio. Instead, there are amazing companies that what they do is SDRs, different modems, different radio systems with different frequency ranges, and again, using private cellular communications, or use CBRS, or use the 2.4 bandwidth, or use satellite communications, aggregating everything into this logical layer of connectivity. What happens is that you potentially able to use frequency ranges from 600 megahertz to 6 gigahertz. For example, with T-Mobile, you'll have the 600 megahertz, and in 5G and LTE, you have also bands in the 5.9 gigahertz spectrum. So having this kind of wide frequency range, it becomes a real challenge to jam everything in such a big area. And of course, the idea with jammers is that you basically need to be stronger than the other side. And when you're flying a UAS and take it too far, then it sometimes becomes a real challenge to stay the strongest link. But again, changing the CONOPS, if we're not looking about being stronger in the point-to-point link from the pilot to a UAS, but instead we're looking to use from the UAS to leverage all the local communications, if it's public cellular or satellite communications, then again it becomes much harder to jam the radio. Another use case we saw is just to use tethered drones to have an instant surveillance towers. The challenge is, I think, quite obvious. As you're getting into battlefield, you need to have quick lookouts, and to build something that is full tower, then that takes time, and sometimes it's not really feasible. And you also want to move it and to be mobile as possible. Tethered drones are perfect for this kind of mission. You can just have tethered drone wherever you want, portable and mobile, and just have it. You use it for just as a lookout or perimeter security. And what we found out is that having this kind of reliable connectivity for these use cases provide you a couple of different stuff. One is the ability to transmit this video also to remote control center. Again, use it as a lookout. The idea is not that it will stay locally, but that it will somehow go to a certain video wall. And with this concept of aggregating multiple communication paths, then you can place it on this kind of drone or on its ground and just control it and send the video to the control center. And again, when we're talking about control it, this is really important because in the battlefield, you want to avoid as much as possible having people in the front line. If you can do things, control things remotely, then it's better and it's safer. So having this ability to connect the telemetry, the control, and the video to a system that is able to utilize all the available spectrum to send the data to the control center, it makes it a very good and safe solution. Another thing that related use case to it is that in some situations, you might want to use a tethered drone as, for example, for perimeter security. And once you detect something that is suspicious, you're able to detach from the tether and go to this detected target. But in order to do it efficiently, you don't want to again get a disconnect of video and C2 during this migration. And one of the things that we demonstrated, again, started with commercial industry and adopted also by the defense industry, is that when you use a halo, for example, like ours, that is able to again encapsulate all different communication paths. One of the communication paths can be the tethered cable, and then once you're detaching from the tethered cable, actually you're not disconnecting from anything, because in parallel to this tether, you also have the public cellular or another type of radio that is connected with it. So again, the same kind of concept, detaching from the tether and go to the area of interest without losing connectivity in this migration. Another important use case that we understood is this very important need in sending the video from the field to the decision makers. Now, it doesn't have to be from the UAS itself. It can be also from the pilot, from the ground, from the GCS. But the main idea here is how to bring the video to the decision maker. It's very hard from a decision maker to operate and communicate with field personnel and with the pilot or with operators and start to understand the situation. The more that this feed can be in real time and can be right in front of the eyes of the decision makers, then the decisions can be taken faster and safer because there's more information. So it can be much more accurate and of course quicker. So again, for FPV drones, for example, that are typically smaller, then instead of transmitting from the drone itself, we can, for example, get the video from the ground side and transmit it to the HQ, again with the same way, leveraging all the communication paths. That's it for now. So this was basically about how to take this success and understanding of what we did or the advancements of the connectivity in the commercial industry and how it is adapted and how relevant it is for the defense industry. And I'm free for questions.
Thank you so much, Roi, for that excellent presentation. We'll go ahead and begin our Q&A. I'll now open the session up to the audience to ask questions. We already have some that are queued that have come in during your presentation. As a reminder, you may submit a question using the Q&A, which can be found next to the chat button. Just type your question, hit the submit button, and away we go. So, Roi, I'll start with a question. Presumably, in terms of like spectrum, communication, devices, things like that, you may have SIM cards involved. Who provides the SIM cards in terms of the Halo or other Elsight products?
Yeah, so when we're talking about public communications, public LTE or 5G carriers, then of course you need to have SIM cards. This really quite flexible. Some customers may bring their own SIM cards and just plug them to the Halo, and the Halo will automatically dial and connect to the internet. In some situations, Elsight can also offer SIM cards. For example, in many places in the world, mainly in the USA, but also in Europe, Elsight provide also the SIM cards and data packages, and of course we offer this solution as well.
Fantastic. And I think you just answered another question that had come in. Does Elsight offer data packages? So that is something you offer alongside SIM cards. Wonderful. We have a question that actually we have a similar question that's come in multiple times regarding the multiple communications possibilities. So if one communications link is being jammed or is interrupted, will the UAS operator have the ability to choose the next communication link, or will the Halo automatically choose the next secure network to continue the flight?
So it really depends on the pre-configured policy. There are a couple of different policies for how to use. I will start with the one of the typical configuration policy, which is just to parallel the communication across all the communication paths, and depends on the different application. Let's take one of the best practices that we have, again, for commercial industry, but it's really the same, maybe even more relevant to defense industry. You typically on UAS, we have two typical data applications. We have the C2 traffic, which is the most important traffic, and it's usually low in throughput. And we also have video, which is in most times less important than the actually C2, and it's a little bit more heavier. So instead of having one policy of should we just duplicate the traffic or should we split it across all different paths, we allow this kind of policy per type of application. So we're able to create multiple aggregation pipes, multiple different VPNs for different application sets. So for example, for the C2, instead of actively or instead of reactively act after we detect a center failure, we just decide to duplicate the C2 traffic across all the communication paths. So the deduplication at the GCS side happens in real time per packet. So when one communication path fails, then the operator doesn't even notice it as long as another communication path works, because we already received the packets from all the communication paths at the same time. This is really also one of the only ways to do it with no downtime when combining siloed networks. Because if we have the public network together with an SDR, then if I need to wait for detecting failure in one link in order to start using another one, that will be a few seconds. So instead, we just duplicate the traffic across the point-to-point network and the public network. And this is how we're able to will create make a very good and seamless transition between the different communication paths.
Okay, fantastic. I appreciate that. The next question, kind of two-parter question, and you've touched on part of that already, I believe. So how does Elsight know which cellular providers to use, and how does the operator know where the strongest cell coverage is? So if they want to use the Halo to operate, beyond visual line of sight in LOS, like how do they know where they're going to have the coverage they need using the Halo?
So yeah, this is quite a good question, because the idea here is with one of the differences between SDR to public cellular is that with SDR, with all of its point-to-point or line of sight flaws, it's more predictable. Putting jamming aside, is quite predictable understanding and planning a path that you know where it's going to work and when it's going to fail. But when working with public cellular, it is not your infrastructure, it's third-party infrastructure. So in order to do it efficiently, one of the things that we have in the Halo is, and I touched it a little bit, is the ability to automatically record and log the signal levels that we're detecting from different public cellular carriers. And what we're doing is not only that we record it and provide this interface to the users to download it and get it, but we also analyze it and prepare an accumulated signal heat map. So you're able to get a full understanding, a full visualization of what is the signal, what are the signal levels from all the different carriers with all the different technologies in your operating area. And more flights that you'll do, you'll have more and more data in this area. And this information, again, as an example of adopting commercial requirements, this is one of the things that regulator wants. Regulator in the commercial industry wants operators to fly in places where they have they have a certain idea of what would be the signal level. So we designed this solution for drone operators to log and to understand where they can fly safely. So this is exactly the same concept that is applied also to the defense industry, that using the same tool, they can create this signal heat map and know exactly where would be I wouldn't say it's 100%, but that's a heuristic of where would be the highest chance of flying safely.
Right. This next question piggybacks off of that perfectly. So you mentioned the sort of heat map so users can understand where the greatest coverage will be. The question is, what if I want to change the location of my UAV flight paths to another country?
So when working with a public cellular, then this is quite flexible, because again, we talked about SIM cards, but SIM cards can change their identities. Sometimes it's SIM card with a roaming package that is able to work with just to, like we do with cell phones, with mobile phones, that we travel to another country and then we have a data package. Or that we're able to change the identity of the SIM card. So one of the things we have in the Halo is modems that are supporting the eUICC, which is able to load and replace profiles of the SIM cards. And thankfully, because you have multiple communication paths, then you have the luxury, let's call it, to replace an identity of one modem or another modem gradually. And again, gradually disconnecting links, replace them with a different identity, and then start working with another identity in another country.
Awesome. So very, very versatile. Next question for you. What are the use cases for setting up a private cellular network? And is that applicable and usable by the Halo?
Yeah. So private cellular network is we see become more and more popular in the IOB, the Internet of Battlefield. We see it with ELTA, Israeli Aerospace Industry Solutions, and we'll see it with Lockheed Martin solution, the 5G.mil, and it's really taking all the advantages that we know from the cellular technology, like with the 5G, which is able to have multiple users sharing a certain frequency with in high bandwidth and with the ability to prioritize different users. All of this is exactly what also defense sector needs in the battlefield. And what we're seeing with the Halo is that it's really a force multiplier, because now you have the ability to work with SDR-like solution, like a point-to-point solution, but you don't need to add additional hardware. The same hardware that you use for public cellular can be used also for the private communication paths. So in some portion of the path, maybe use the point-to-point private cellular, and in another portion of the path, you'll work with the public cellular. Having the ability to soft handoff between the private cellular to the public cellular without having any disconnect in the middle, this is quite unique to Elsight with our Halo. And again, the most important thing is not to get to the place where you get disconnected from the C2 and video, but having it seamlessly steered and handoff between the point-to-point private cellular to the public cellular.
Wonderful. That's fascinating and really exceptional, the handoff that you're describing there. The next question I have is a little bit technical. What is the maximum speed of the bonded link?
So the speed, and also the different characteristics of if it's the speed or latency or packet loss or quality, they're actually derived from the quality of the links that are encapsulated within the aggregated layer, and I would say also the different policies. If we're duplicating the traffic across all the different communication paths, or we're splitting the traffic across all the different communication paths. But this is really a question also of where you want to put the weight on bandwidth or on reliability. Okay, it's kind of a scale that you can take it to either side. I would say that technically, when we're looking at the generally at the aggregation as a tool, then it has very good advantages. It has some limitations for different applications. So I would say that we're usually, and again, comes from the commercial world, we're not tending to work in speeds that are higher than 80 or 100 megabits per second. This is not a use case that is relevant for our types of applications. Typically, what we're seeing as the needs of UAS is somewhere around between half megabit per second to 5 megabit per second. Sometimes it's a little bit more, and by aggregating multiple communication paths, then again, depends on the policy, you're surely able to get this kind of speed.
Wonderful, thank you. Next question. Broadly speaking, is this solution similar to session-based routing?
Not necessarily. Session-based routing is something that is something that is more related, for example, with load balancers. When we're talking about load balancers, that it means that, for example, when you start to watch or send a certain video or go to a certain website, then this session will go through one of the communication paths, and if you open another session, then it may go through another communication path. What we're talking about here is to take one data feed and split it or duplicate it across all the communication paths. And the way we're doing it is with our, again, couple of different options here. Of course, it's different. For example, if we're getting the telemetry not from IP, but from a UART port, then we're reading the telemetry from the UART port as a serial communication, and then send it over UDP, for example, to the destination over our VPN. But when we're talking about IP traffic, then what we're doing is we're creating a VPN that simulates as if you have a very long LAN cable, that one side of it is connected to the on the UAS side to the switch or the companion computer or the mission computer, and the other side of this long virtual cable is connected directly to the GCS. So you have full IP network, and you can continue to work exactly as the application expects to work. But all the traffic internally goes through our tunneling that splits or duplicates the traffic across all the communication paths. And this is the idea here, is not to change the behavior of the application, but to make everything so simple to the user that it'll just work as is, and will take all the complexity and implement it internally in our logical connectivity layer.
So definitely some differences there. Next question, more technical. What size of drones can use your communication? So what's the weight for the communication system?
So the weight of our Halo, which is with the built-in, without any external equipment, so with the built-in LTE or 5G communications, it's approximately around the 93 or 100 grams, more or less. Depends with or without heatsink and things like that. So I would say roughly around 100 grams. Now, if you want to combine it with satellite communication or with SDR or things like that, then of course it's external communication, external radios that are connected to the Halo through its Ethernet ports or USB or RS-232 or UART ports, or even Wi-Fi technically. So all of these options or interfaces are to communicate with the external radios. But if we look on the Halo itself, it is around the 100 grams.
Gotcha. Thank you. Another technical question that I think was answered in the Q&A, but just make sure it's answered. What's the power draw as well, just generally speaking?
So the average power draw is 6 to 6.5 watts. So it's pretty low and quite negligible when comparing to the actual drone and the other systems it needs to operate.
Wonderful. And then maybe, let's see, the last question we may have time for. Other questions will be answered individually. Roi, we'll get back to you folks, but has Halo already been used on real battlefields? And if so, where and when?
Yes, from the obvious reasons, we cannot tell exactly what it's doing, but in the major conflict areas in the world right now, it's in use, of course, in the different use cases we mentioned, and some of them were publicly announced. For example, one of the things that we announced with a certain collaboration with a company called Robotican that is able to, it's actually a counter-UAS solution that for all of their components, they need reliable connectivity. So on each of the nodes in their system, there is a Halo device that the Halo device is connected to two different private LTE sites together with two public LTE sites. And this way, we're able to, again, hand off between each of the nodes is mobile and is able to migrate between the private to multiple different private networks and the public networks, and the communication is basically flawless.
Wonderful. Thank you so much. So before I close things out, I do want to give you a moment just to kind of close things out yourself, offer some final thoughts. And also one question asked you to reiterate how you know which cellular providers to use. So in your conclusion, maybe to touch back on that and wrap us up.
Yeah. So one of the things just to talk about how we know which link to use or cellular provider to use, then some of these will be as from the pre-flight planning, for example, again, using the heat map, the cellular signal heat map, then you could see what will be the strongest cellular providers that are relevant for this area. And the second thing is in real time. When we're splitting the data across all the communication paths, and usually across the cellular communication paths, then in real time on each of the communication path, we also have a feedback link that we're able to monitor in real time the packet loss, congestion levels, half round trip times, and using this real time data, we're able to steer the traffic and rebalance the traffic that was split across the communication path. So something that we start maybe with equal transmission between the communication paths, we can end up having 10% through communication path A, and 20% through path B, and so on and so forth. And it's really dynamic and changing in real time.
Wonderful. So thank you so much. And audience, thank you so much for those wonderful questions. Good balance between the broad and technical. Really appreciate everybody. So on behalf of AUVSI, I'd like to thank Roi for today's excellent presentation and discussion, and Elsight for their generous sponsorship of this webinar. Attendees, you'll receive a link to access the webinar recording within the next week or so. Another exciting feature is that all webinar recordings are now available on AUVSI's learning and engagement platform, Able. So when you visit Able to view the recording, please take a moment to look around and visit our active courses, check out archived content in the library, share some industry news or what you're working on in my community, and connect with other industry professionals, and even more. When you receive the viewing link, there will be instructions and information about accessing the recording and slides in Able. If you do have additional questions or comments, please email us at education@auvsi.org. And lastly, today's program is copyrighted by AUVSI with all rights reserved. Thank you all so much, and have a great rest of your day.
Thank you.